Today we are walking through the paper titled Solve the Loop Attractor Models for Language and Reasoning.
What problem are they trying to solve first, before we get into the model?
The paper starts from loop transformers. These models reuse the same block several times, so a token representation can be refined step by step instead of passing through a fixed feed-forward stack once.
So the loop is useful, but not easy to train?
Exactly. Earlier recurrent language models can be unstable, expensive to optimize and deploy, and often tied to a small fixed number of recurrent steps. If you unroll every loop during training, memory grows with the number of steps.
What do the authors change to get around that?
They introduce attractor models. A backbone module first makes an initial output embedding. Then an attractor module repeatedly refines that embedding until it reaches a fixed point.
On this diagram, what should I follow from left to right?
The input text goes into the backbone on the left. That gives a first guess for the next dictone distribution. The attractor module on the right keeps applying the same refinement tool until the update becomes small. Then the final embedding is turned into prediction scores. The first equation defines that initial proposal. The input tokens are embedded as x tilde, and the backbone transformer maps those embeddings to y tilde 0.
Then the attractor module starts from that first guess.
Yes, the second equation defines a refinement step. Each new y tilde is computed from the previous y tilde and the original backbone proposal, so the attractor can improve the guess without forgetting the input condition starting point. The fixed point equation makes that stopping point explicit. Instead of saying run exactly 2 loops, the model solves for an embedding that maps back to itself under the attractor update.
Why does writing it as a fixed point help training?
Because the backward pass can use implicit differentiation. The training update depends on the equilibrium and the local Jacobian, so the method does not need to store every intermediate recurrent activation.
So the solver can run as long as needed, but training does not keep the whole path?
That is the key engineering claim. The model gets adaptive refinement from the root finder, while the implicit backward pass keeps memory constant as the effective depth increases.
How is that different from just looping the same language model block a fixed number of times?
A fixed loop decides the number of updates before seeing whether the representation has settled. The attractor model checks the residual, meaning the size of the change between two successive embeddings, and stops when that change is small. That matters because easy tokens do not need to pay for unnecessary refinement, while harder cases can use more solver work. The paper frames this as adaptive computation tied to convergence, rather than a handpicked occurrence depth. Now we can move to the evidence. The authors test two regimes: large-scale language modeling, and small models on hard reasoning tasks that require iterative computation.
What does the language modeling result say?
On this plot, lower and farther left is better. Across 140 million, 370 million, and 770 million parameter scales, the blue attractor model points sit below the transformer in Part K, E baselines at similar or lower training compute.
Can you make that comparison concrete?
The paper reports up to a 46.6% perplexity improvement and up to a 19.7% downstream accuracy improvement. It also highlights that a 770 million parameter attractor model beats a 1.3 billion parameter transformer trained on twice as many tokens. The point is not just that the model is larger or trained longer. The claimed Pardo improvement is that it gets lower perplexity while spending less training compute than the nearby baselines.
Does that mean the result is mostly about efficiency, or mostly about accuracy?
It is both, and the figure is useful because it puts them on the same map. The y-axis is test perplexity, so lower means a better language model. The x-axis is training compute, so farther left means cheaper training. The blue curve being below the gray and orange curves means the attractor models are not merely trading speed for worse quality. They move the frontier toward less compute and lower perplexity at the same time.
Where does the constant memory claim fit into those results?
It explains why the method can train deeper effective refinement without paying the usual unrolling cost. Standard looped models backpropagate through each recurrent step, so memory grows linearly with the number of loops. The implicit backward pass avoids storing that whole trajectory.
And the reasoning tasks test whether the loop helps with step-by-step computation.
Yes, the authors train small models with roughly 1,000 examples per task, and require the model to predict the full output quite directly rather than decode it one token at a time.
What happens on those harder tasks?
The strongest attractor model reaches 91.4% accuracy on Sudoku Extreme and 93.1% on Maze Hard. The same chart shows several baselines at 0, including frontier models on the standard transformer in this setup.
How should I compare the small attractor bars against the recursive reasoners?
On Sudoku Extreme, The 27 million parameter attractor model is above the 7 million parameter attractor model and above the listed TRM variants. On May's hard, it rises to 93.1%, while HRM is at 74.5% and TRM 7 million is at 85.3%.
Why did the 0 bars matter here?
They show that this benchmark setup is not solved by simply being a famous general model or by using a standard transformer. The tasks demand structured iterative computation, and the attractor models are designed to refine an answer until it stabilizes. The comparison is also about scaling inside the small model family. The 7 million parameter attractor model is already competitive on these grids, and the 27 million parameter version jumps much higher on most tasks. The last important claim is equilibrium internationalian. After fixed point training, the backbone's initial output embedding moves close to the equilibrium, so the solver can sometimes be removed at inference with little degradation.
So the loop is still used for training Pasha, but inference may become cheaper.
That is the interpretation. The attractor solver gives a target equilibrium during training, and the model learns to place its first proposal close enough that much of the iterative work is internalized.
Is that different from saying the solver was unnecessary all along?
Yes, it is different. The solver supplies the equilibrium target during training. The surprising part is that fixed point training reshapes the backbone so its first output starts closer to that target later. That is why the authors call it internationalian. The repeated refinement is not just an inference trick. It becomes a training signal that teaches the model to approximate the refined answer earlier.
What is the final takeaway for someone who only remembers one thing?
The paper argues that recurrent refinement becomes practical when it is treated as a fixed point problem. Attractor models refine embeddings adaptively, train with constant memory in effective depth, and show better compute performance trade-offs in language modeling plus strong gains on compact reasoning models.
Nice, that makes the contribution clear.
That wraps up this paper walkthrough.